I will speak about trabecular-bone anyway. So trust me, the part this fracture is a bit easier than what I'm going to present. I've already made an announcement that we will be looking rather on the just about the bone adaptation. And since I can give you our ideas how we deal with the fracture if you want, but this is so it's slightly different to what was initially announced. And generally, yeah, this is outline, but so just clearly it is for the short presentation. It doesn't need to be long. So for those who just mostly dealing with the non-biomedical materials, a short introduction into the bones. So we have, this is a femoral head, the largest bone in our body, and you can see here that generally we have a cortical bone, this yellowish part, which is a dense one, and so on, and it is the strongest, protects, and so on. And on the other hand, we do have a trabecular bone. This was prepared by my PhD student who likes animations. I'm clicking too much. So this is the trabecular bone. You see the spongy type of the material, or highly porous one, and what's not. And inside this part, we also have the bone marrow. And the bone marrow suggests, you can consider this suggests as a very soft liquid. And the most important part, and these are trabeculae, which have been formed. These are the, so you see this magnification, the color is nearly the same. They're nearly made of the same material as the cortical bones, which is from the osteons, but they are just relatively small and fine. And generally, the most important part which we would like to look at is what is happening with this bone in our life. And generally, it was pretty well established, and the famous Wolff's law from the 1896 just states that generally you apply the load or you apply the displacement. It depends, and you will see why. And you will have some developments in the bone. If so that's why you load it, it is the density generally becoming higher, stronger, and this is the formulation of the Wolff's law, that the alignment is generally along the main direction of the loads. And as a result, for instance, you can see here that depending on the position, and this is still the top part of the femora, you can see that the position of the loading directions would be different. And so just this is compared with what is happening, and so just this is the idea of motivation of this study. Another motivation, when it is, and this was studied in the Soviet Union for a while, people are exposed to the conditions of the weightlessness, then so just obviously there is no permanent load, and the bones, they are becoming thinner, and you can see what is control part and what is unloaded part. So for those of you, just please do exercise, because generally if you are in the bed, so just for 6 weeks, you can lose up to 10% of your bone mass. So that's why it is that serious. Good. So now, generally how it is being done. So we have, this is the cross-section of the bone, as you can see somewhere here. And generally what we see that after the process of the so-called adaptation or remodeling, so we have a system which is better developed. And this is the story behind this presentation. The idea was always that the laws, or the Wolff's law, it is not a law, it's an observation. So people of our backgrounds in mechanics, we were thinking, what can affect this? And historically, there were several models developed here that the stimuli which are affecting the mechanical stimulation of the bone adaptation these are practically whatever you would like to choose, and from the standard set of the parameters. And people have done different type of research, so you can get the high resolution micro-CT images, and you can see that the bone can either form, or it can, this is the orange part, or the purple one, it can resolve, or it can diminish. Interestingly enough, both processes, they can happen simultaneously, obviously in different parts of the microstructure. And this is so, how can we deal with this mechanically? And the presentation will deal here with the relatively simple model, simple geometries, but the most important models. One is based on the von Mises stress, another is on the stress and energy density, and is the maximum principal stress, and we will use these acronyms in the future study. So, what is happening here? If we are looking, for instance, at the remodeling process, this is a typical one of the typical curves. There are several major groups of this, which shows that depending on the of the state of the loading, we are either in the so-called lazy zone, where most of the physiological loss happening. So the bones, they usually stay the same. They neither grow nor resorb themselves. And clearly, we have when there is not enough stimuli, we have this red part of the bone resorption, and we have beyond this, we have a bone formation. So it is the parts of these curves, they can be different, and there are different approaches which are dealing with this. And then we can introduce the idea also of what is happening. And the point is that most of these processes, clearly, there is biophysics, biochemistry, which is much deeper. There is, so there are biochemical reactions, then the cells are being used, and there are osteoclasts and other types of the bones which are responsible for this. But for the purposes of mechanics, it's very hard to go from that level. So we can write a couple of the equations, but it wouldn't help. So that's why we can still stay within the domain of the macroscopic mechanics. So as far as it happens on the surface, we can consider the situation which was started in the works of Adachi, when we are looking what is happening on the surface in the nearest area close to the specific part, and depending on this, either we can have the, for instance, additional element is being added here, such as the bone is being formed, or it can be removed, it is being resolved. These are the simplest acts at this level. So, and let us now go, after this introduction, how it is being done. So this is the very simple in terms of the geometry, but still reflected the major features of the trabecular structure situation. And so this is what we are dealing with. This is the cross section, which corresponds to this type of the real life bone. And these are the parameters. So just what you need to remember, roughly it is the thickness of the trabecula, which is just 1/4 millimeter or so. The length is twice as this, and this angle, so clearly everything's changing, but this is a typical one which was measured in reality. And now we are doing the following part. So we are introducing the two-domain system. One is the bone, which is surrounded by the marrow, and clearly bone is, just for these purposes, deformations are small, and we have the most important part, as I've already mentioned. You should look at the difference in the stiffnesses of the bone and bone marrow are roughly 3 orders of the magnitude. So that's why the marrow is not a load-bearing component, but it is rather being used as a source of the formation of the new bone, or oppositely the bone can resorb into that. Good, so far so good. So this is the model. So clearly, since we need to apply, because we are doing the finite elements, boundary conditions, and we apply the load, and so just this is all described properly, that there is no problem with doing this, and we are just doing the following. We are linking together the abacus, and we are producing the with Python the subroutine, and they are linking together. So just we are solving the problem, distribution of the respective parameters, and I've said that there are different of them. We'll deal with this. Then they are interacting. The signals are going here. We are describing, looking at these just effects of the stimuli on the mechanical stimulation. So looking at what is happening, whether it is lazy zone, so just growing, or rather so just being diminished, and then so just it goes back, and we update this, and this is so just in the nutshell what you will see. And what you will see, so just as always, is this is okay. Too many animations for my liking. Okay, these are the results of 3 simulations. Form is so just strain energy density and major principal stress. So just then the load is applied for so just vertically to the bottom. And look what is happening. So you see that the transformations are immediately different, because they are based on the different stimuli. So don't worry, it's 43 seconds, not minutes. So the important point is clearly, because this transitional part, it is it's pretty well known that all the models there overshoot at the beginning. But you see now that we are going to the end of the simulation, that they are becoming a bit, now it's all finished. And you can see that generally there is a similarity, so just in the parameters like the trabecular thickness, but there are also still the differences. The difference between them is different. There is a change in the connectivity, and so there are similarities which I mentioned. So just instead of the V shape, we've got 2 columns, because this is the most, so just all mechanics, specialists in mechanics, they understand that it's the best way to resist the structure from that point of view. And we have so just also some differences which are shown here. And so if we are looking now at some of the typical characteristics, which are so just for you to understand, before engineers started dealing with this, people so just clearly specialists who were doing histology and what's not, they have introduced a plethora of different parameters which characterize trabecular-bone. So this it depends, it's up to a dozen. So that's why this definition suggests it's like roughly, in our terms, it will be a volume fraction of a bone from the composites, and this is trabecular thickness. So this is established parameters, not a mechanical one. I'm bringing it here, and you can see here that effectively we start from here, and that we are so just what we are having. This is just some changes, and then it stabilizes, and we are after the intermediate stage we are reaching the equilibrium. But there are still some differences which you've seen. And this is for volume fraction, and this is for the trabecular thickness, as you can see. So we can also look very quickly so just into some details. So now you can see this is initial stage, this is the final stage, but with the distribution of the respective parameters. For me, the stress energy density, and major principal stress. And you can see so just that generally a load is being defined by the level of the non-uniformity, but also the final state that they are not uniform systems in all the parameters. These are different in different models, and now we also have the possibility to look at these are 3 three realizations, as you can see, but this is a comparison of these specific parameters in the equilibrium state. So you can see that also these are not just the same, which would be just clearly not strange. So generally, and at the moment, these are only partial conclusions, suggest that we can see that the maximum principal stress provide a more uniform situation in the middle part of the specimen, while the others are shown the higher level of the non-uniformity of all the three parameters. But so just as a result, this is what is happening. And clearly, so just a very short conclusion here. So this is how the bone can grow. Now, going back to the original title, which is not being presented because the title was slightly changed, about the fracture of this. So what we need to understand is that generally there are positive and negative part. Positive part is that fracture usually happens instantaneously. So the scales that we are shown here, these are months, if not years. It all depends upon the stimulus. So that's why interaction of the remodeling with the fracture does not happen. So a part that you are looking at the healing is post-fracture process from that point of view. So generally, you can always look at this, and the usual thing what we are doing, we are using just either the ideas of the fracture mechanics, or we are using the ideas of the continuum damage mechanics, because we do have the full fields of the stress and strain parameters, and we are looking there just at the situation where the crack can stop. I will also show a little bit, not the cortical bone, but the fracture of trabecular bone and the cortical bone in another presentation today and here. Thank you very much for your attention.